Module 20C, we're going to focus on balancing redox reactions. So you guys learned how to balance reactions in the beginning of first semester, or near the beginning of first semester. Redox reactions just work a little bit differently because remember in redox we're looking at the transfer of electrons. So it can get a little funky when you're trying to balance them. So we're going to focus on how to balance these, and it does depend if they're done under acidic or basic conditions. So you must know up front if it's acidic conditions or basic conditions. No matter what, you start out balancing them the same way. If they're acidic, it's just one step less. If they're basic, we have to do one more step within the reaction, and we'll talk about why. So the general rules involved with balancing redox reactions. First, go ahead and assign oxidation numbers to all of the atoms and identify the substances that are being oxidized and reduced. When I say all of the atoms, when you're first getting used to it, it's best to identify the oxidation state of truly all atoms. Once you've got a little practice under your belt, you're going to be able to quickly identify which species are being oxidized or reduced, and at that point, you don't need to identify it for everyone, or for every atom. But initially, it's best to just go ahead and follow that practice. You should separate the overall reaction into two half reactions. You'll have your reduction reaction and your oxidation reaction. You're going to balance the half reactions with respect to the individual atoms in this order. Balance everything, every atom you have, except hydrogens and oxygens first. Then you balance oxygens by adding water to the other side of the reaction until your oxygens are balanced. Once that's done, you balance your hydrogens by adding H+ or protons to the opposite side of the reaction to balance out your hydrogens. You're going to balance each half reaction with respect to charge by adding electrons. You add these electrons to the more positive side. Does your oxidation number equal the number of electrons? It's a quick check you can take. Multiply the half reactions by factors that equalize your electrons. Add the two half reactions together and check yourself. Is the overall charge the same on both sides of the reaction? If the redox reaction occurs in acidic solution, you're now done. If the redox reaction occurs in basic solution, though, you need to add enough hydroxide ions to both sides of the equation to convert all H+ to H3 or H2O. And you'll see why when we do a couple examples, but bottom line, we can't have H+ floating around in a basic solution, because what happens to H+ in basic solution? It's neutralized. So let's go ahead and work some examples. First, balance the following reactions under acidic conditions. So you do have to find, first step, assign oxidation numbers to all of your atoms and identify what's being oxidized, what's being reduced. P4, oxidation state is 0. HNO3, I find it's most simple to separate these out into their individual ions, which gives me H+ and NO3 minus. So I see my H is +1, my nitrate is NO3 minus. Oxygen is -2, there's 3 of them, so it's an overall -6 charge. There's a -1 charge here for the overall ion, which means nitrogen must be +5. H3PO4, I'm going to follow a similar process. That would give me 3 H+ and 1 PO4 3-. So my H is still H+, or still +1. Oxygen, -2. There's 4 of them. Overall -8 charge, or a -8 charge from oxygen, but overall -3 for the ion, for the polyatomic. So there means that phosphorus must be +5. And NO, the oxygen is -2, so the nitrogen must be +2. So when I look at this, I see my phosphorus has changed from 0 to +5, and I see my nitrogen has changed from +5 to +2. If I'm going from 0 to +5, I have lost electrons. Remember, oxidation is loss. So phosphorus has been oxidized. For nitrogen, I'm going from +5 to +2, which means I have gained electrons, and gaining electrons is reduction. Now I'm going to go ahead and write these out into their individual half reactions. So I've got P4, solid, giving me H3PO4. I need to balance out all atoms except oxygen and hydrogen. I have 4 phosphorus on my reactant side. I need 4 phosphorus on my product side. So I'm going to go ahead and put a 4 in front of there. Now that I've balanced everything except hydrogen and oxygen, I need to balance my oxygens. You balance oxygen by adding waters. I have 4 oxygen on my product side. I have 0 on my reactant side. But don't forget the 4 in front. I have 4 in that PO4. I have 4 H3PO4s though. So what I really have floating around in solution right now is H3PO4, 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 H3PO4. That gives me 16. And I say that because I often forget when I'm doing redox reactions to look at that. Why do I forget? Don't know. I remember when I'm doing regular reactions, but redox reactions I often forget. So please make sure you're paying attention to those coefficients out front. You really need 16 waters here to balance this out. Now I've got 4 phosphorus on each side, 16 oxygen on each side. Now I need to balance my hydrogen. This is 32 hydrogen. This is 12 hydrogen. I'm going to balance hydrogen by adding H pluses. I need 20 H plus to balance out my hydrogen. Now I have 32 H plus on each side of the reaction. Last thing I need to do is balance my charge. Over here, I have an overall charge of 0. P4 is 0, H2O is 0. Over here, I have an overall plus 20 charge because of the 20 protons. So I'm going to add 20 electrons to balance that out. Now I have a 0 charge on both sides of the reaction. My oxidation reaction is balanced. Let's go ahead and look at your reduction reaction. I've got HNO3 going to NO. First, balance everything but hydrogen and oxygen. And I see I got 1 nitrogen on each side, so that's already balanced. Next, I'm going to look at my oxygens. I've got 3 oxygen on my reactant side, but only 1 oxygen on my product side. So I'm going to say plus 2H2O. That has balanced out my oxygens. Now I'm going to balance out my hydrogens by adding enough hydrogens to one side to balance them out. Reactant side, I have 1 hydrogen. Product side, I have 4. So I'm going to say plus 3 H plus on my reactant side. Now I've got 4 hydrogens on each side. Last thing I need to do is to balance my charge. This overall charge is plus 3, while this is 0. So I need to say plus 3 electrons. With those 3 electrons, I now have 0 charge on both sides of the reaction. Now that I've got everything done, I need to equalize my electrons, because what I'm going to do is I'm going to add these 2 reactions together to form the overall redox reaction. But when I do that, I cannot have electrons in my final reaction, in my final overall balanced reaction. Electrons cannot be there. The electrons have to balance out because the electrons transferred between the redox reaction have to be equalized, right? If they're lost at the anode, they have to be gained at the cathode. If I've lost electrons from one species, the same number has to be gained by the other species. So I'm going to multiply these by a factor to equalize my electrons. On my oxidation reaction, I'm transferring 20 electrons. My reduction equation, I'm only transferring 3. You need to find the lowest common multiplet of these. I'm going to multiply the top reaction by 3 and the bottom reaction by 20. That's going to give me 3 P4 plus 48 H2O, giving me 12 H3PO4, 60 H plus, and 60 electrons. Do the same thing to the reduction reaction, but multiplying through by 20, I'm going to get 20 HNO3, 60 H plus, and 60 electrons. Giving me 20 NO and 40 H2O. I'm going to shrink this down a little bit for some space. Move this up. Now we're going to add these together, but when we do that, we're going to cancel things that are present on opposite sides of the reaction because they cancel each other out. I have 60 electrons and 60 electrons. I have 60 H plus and 60 H plus. I have 40 waters with 48 waters. That's going to leave me with just 8 water. Everything else remains constant. The ending result is 3P4 solid, 8 waters, and 20 HNO3. It's going to give me 12 H3PO4 and 20 NO gas. This is your overall balanced redox reaction. So I split them up, I assigned oxidation numbers, I split up the reactions based on what was being oxidized and reduced. I balanced everything except hydrogens and oxygens. I balanced oxygen by adding water. I balanced hydrogen by adding protons. I balanced the charge. I equalized the electrons from both reactions. I added the two reactions together and cut out anything that was on both sides of the reaction. Let's work some more examples. Balance the following under acidic conditions. H plus MnO4 minus plus SO2 giving me Mn2 plus and SO4 2 minus. Okay, so H plus 1, oxygens are going to be -2, which means that manganese here is +7. SO2, the oxygen is -2, which means the sulfur must be +4 because there's 2 oxygens. Mn2 plus is +2. SO4 2 minus, each oxygen is -2, which means the sulfur must be +6. I see my manganese has gone from +7 to +2, meaning it's been reduced. It gained electrons, the charge went down, and my sulfur has been oxidized. It lost electrons, its oxidation state increased. So my oxidation reaction, SO2 going to SO4 2 minus. Let's go ahead and just balance that one out quick. 1 sulfur on each side. Cool. Got 2 oxygens on the reactant side and 4 on the product, so I'm going to say +2 waters. Now my oxygens are balanced. I'm going to have to add +4 protons to balance out my hydrogens. And now I need to balance out the charge. Over here, the charge is 0. Here I've got -2 +4. This is overall +2, so I'm going to say +2 electrons. You can only add electrons, nothing else, because you're transferring electrons. Now I've got 0 charge on both sides of the reaction. And my reduction reaction, MnO4 minus, giving me Mn2 plus. I'm going to add 4 waters to balance out my oxygens, 8 protons to balance out the hydrogens, and now I have a +2 charge over here, -1 and +8, so +7 charge over here. I need to add 5 electrons to balance out my charge. I need to add these together, but first I need to normalize or equalize my electrons. Transferring 2, transferring 5. So I'm going to multiply this reaction by 5 and this reaction by 2. 5 SO2 plus 2 H2O, giving me 5 SO4 2 minus plus 4H plus, helps if you multiply, plus 20 H plus, and this should be 10 over here. I apologize. Shouldn't do these things when you're tired. So 5 is multiplied. 2 times 5 is 10. 5 5 times 1, 4 times 5, let's see, and 10 electrons. Now we got the right reaction. And then the second reaction we multiply by 2. So 2 MnO4 minus plus 16H plus 10 electrons, 2 Mn2 plus, and 8 H2O. I'll move this over slightly. What I find is students do best if they line up their arrows because then they can best see when things are truly canceling out. So our 10 electrons have officially canceled. 16 protons and 20 protons leaves me with 4 protons. 8 waters and 10 waters leaves me with 2 water. And it looks like that's everything. So then we just write the resulting reaction. 5SO2, 2H2O, 2 MnO4 minus, 5SO4 2 minus, 4H plus, and 2 Mn2 plus. And you should be able to check that reaction and see that the number of sulfur, oxygen, hydrogen, and manganese on either side of the reaction are balanced, and our overall charge is balanced as well. Balance the following under acidic conditions. Fe2 plus MnO4 minus, giving me Fe3 plus Mn2 plus. So the Fe2 plus 2, Fe3 plus 3, Mn2 plus 2, and in MnO4, each oxygen is minus 2. There's 4 of them, so minus 8. This is plus 7. So this is a little simpler of an equation, but you can see what's being oxidized and being reduced. Oxidation is loss. Iron's been oxidized. Fe2 plus, Fe3 plus. The Fe's are balanced, so hydrogens and oxygens. I just need to balance charge by adding 1 electron. And the reduction reaction, MnO4 minus, giving me Mn2 plus. I do need to add 4 waters here to balance out my oxygens, and 8 protons here to balance out my hydrogens. And now I need to check my charges. -1 plus 8 gives me an overall plus 7. And plus 2. So I need to add 5 electrons here to get my charge to balance out. Now I need to go ahead and multiply the reactions. I need to multiply this top reaction by 5 to equalize my electrons. So that will give me 5 Fe2 plus, giving me 5 Fe3 plus 5 electrons. And the second reaction remains the same. MnO4 minus plus 8H plus 5 electrons, giving me Mn2 plus 4 waters. Check what's going to cancel. And my 5 electrons are all that I can cancel this time. And add up what's left. 5 Fe2 plus MnO4 minus plus 8H plus, give me 5 Fe3 plus, Mn2 plus, and 4 H2O. And it's always good to remember your states. If you have ions, they need to be aqueous because ions can only exist in aqueous solution. And water will be a liquid. What about this example? ClO3 minus plus Cl minus gives ClO2 or gives Cl2. How does that work? It doesn't seem like a very complex reaction, right? Well, let's assign your oxidation states. Oxygen is -2. There's 3 of them, so overall -6, but the ion itself is -1, so chlorine here must be +5. Chloride here, chloride ion is -1, and the Cl2 is 0. So the chloride is being oxidized while the Cl in the ClO3 minus is being reduced. Cl minus going to Cl2. Balance that out, put 2 for 2 chlorine on each side. I have a -2 charge on my reactant side, so I'm going to add 2 electrons on my product side. And the reduction reaction, I've got ClO3 minus, give me Cl2. I need to add waters, 3H2O to balance it out. Oh, I made a critical mistake. I forgot to balance my chlorines first. 2 in front of the ClO3 minus, which gives me 6H2O here to balance out my oxygens, balance out my hydrogens. So I've got 2 chlorides on each side, 6 oxygen on each side, 12 hydrogen on each side. Let's check your charge. There's a -2 here and a +12 here. And this side has an overall charge of 0. So I need to add 10 electrons so that I have an overall 0 charge on both sides. I'm going to multiply this reaction by 5 to equalize my charges, or equalize my electrons in both reactions. That gives me 10 Cl minus to 5 Cl2 plus 10 electrons, and 2 ClO3 minus plus 12 H plus 10 electrons, giving me Cl2 plus 6 H2O. Ten electrons have canceled out, and nothing else can cancel. Nope. Then add up what's left. 10 Cl minus, 2 ClO3 minus, 12H plus, 6 Cl2, and 6 H2O. And again, if you look at all the chlorine, oxygen, hydrogen, and the charge here, everything has balanced out. What about this reaction? Now this note says in basic solution. So we're going to do a couple examples in basic solution. How do those work? Well, they work the same way as acidic, except at the very end we have to add in hydroxide to neutralize all of the H plus that we have in solution. So we've got MnO4 minus plus Br minus, giving me MnO2 and BrO3 minus. The manganese here, plus 7, oxygen, -2, bromine, -1, manganese here is plus 4, oxygen, -2, bromine here, plus 5, and oxygen, -2. If you're unsure about those, please review the videos on assigning oxidation states. Manganese is going from plus 7 to plus 4, so this has been reduced. Bromine is going from -1 to plus 5. This has been oxidized. So let's look at our oxidized equation first. Doesn't really matter which one you do. I just think about it as oxidation reduction reactions. Br minus giving me BrO3 minus. My bromines are balanced, but I need 3 waters to balance out my oxygen. Now I've added 3 waters, that added added hydrogens. Now I need to add 6 protons on the product side. Overall, this has a -1 and 0, so overall -1 charge. -1 here, plus 6, so an overall plus 5 charge. I need -1, so I'm going to say plus 6 electrons. And for the reduction reaction, MnO4 minus, giving me MnO2. Let's balance out my manganese first, or balance. Let's balance my oxygen. 4 oxygen on my reactant side, 2 on my product. So I'm going to say plus 2 waters. Now I need to balance out my hydrogens. I've got 4 hydrogens on my product side, so I'm going to say plus 4H plus on my reactant side. Last thing I need to do is look at my electrons. -1 plus 4, and overall 0 charge. So I need to say plus 3 electrons to balance out my charge. And compare these two. I see I need to multiply this by 2 to get rid of my electrons. So let's rewrite those reactions. Br minus plus 3H2O, giving me BrO3 minus plus 6H plus 6 electrons, and 2 MnO4 minus plus 8H plus 6 electrons, giving me 2 MnO2 plus 4 H2O. Go ahead and make sure everything's canceling out correctly. My 6 electrons have canceled. I have 8 protons here and 6 here. That leaves me 2 protons here. I have 3 waters here and 4 here. That leaves me with 1 water. And everything else has been canceled. Add up what's left. Br minus, 2 MnO4 minus, 2H plus, gives me BrO3 minus, plus 2 MnO2, plus the water. Now this would be correct if it was under acidic conditions, but we're not under acidic conditions. So this is not correct because I cannot have H plus under basic conditions because it just won't exist. We spent enough time on acid-base chemistry this semester that you guys should know you cannot leave things in, you will not have H plus existing if you are in a basic conditions. So what we do is we add enough hydroxide to the reaction mixture to get rid of those hydrogens. So I'm going to add 2 OH minus to each side of the reaction. That gives me 2 waters here and 2 hydroxide on the other side. Those 2 waters, though, need to be simplified with the water that's already in the system. So 1 water here, 1 water there, cancel out. And our final balanced reaction under basic conditions is Br minus plus 2 MnO4 minus plus 1 water, giving me BrO3 minus, 2 MnO2, and 2 OH minus. So you can see it is a longer process if you're balancing under basic conditions, but you have to be aware of what you're doing. You have to be aware this is going to happen. Let's do one last example on balancing reactions, and we'll do this under basic conditions. Cn minus reacts with Ag solid and O2 to give me AgCN2. And I apologize, there should absolutely be a minus charge right here. This is an ion, a polyatomic, or a metal ion here. So let's go ahead and figure out our oxidation states. Cn minus. Nitrogen, again, oftentimes we see it as a positive. Remember, nitrogen can be negative. The more negative the more electronegative that element, the more likely it is to hold a negative charge. Nitrogen is more electronegative than carbon, so nitrogen will be on the -3 charge here, while carbon is +2 for its oxidation state. Silver and oxygen are both zerox, or in their most stable state. And then for AgCN2 minus, I want you to split this up and think of Ag plus and Cn minus. This will be +1, the nitrogen stays -3, and the carbon stays +2. And then the overall AgCN2 has a negative charge to it. So we split this up, and we see we've got Cn minus plus Ag, giving me AgCN2 To balance that out, my carbons and my nitrogens, I need 2 of on each side. I have 1 silver on each side. Now I just need to balance my electrons. I have a -2 and a 0 and a -1 charge, so I need to add 1 electron over here. Now all my atoms are balanced. I don't have any oxygens and nitrogens, so I don't have to deal with that. My electron is balanced. The only other thing I have in here is O2. But there's nothing on the product side yet. It's because it's not balanced yet. To balance my O2, I'm going to say this results in 2 moles of water. 2 oxygen on each side of the reaction now. Now I have to balance some hydrogens because I added hydrogens to the product side. So I'm going to say plus 4H plus. Lastly, look at your charge. This has 0 charge. This overall has +4. So I'm going to say +4 electrons on my reactant side. Now my half reactions are balanced and I need to compare them to each other. To do that, I need to multiply this top reaction by 4 because I want to cancel out those 4 electrons. Rewrite what you got. 8 Cn minus plus 4 Ag gives me 4 Ag Cn 2 minus plus 4 electrons. 4 electrons plus 4H plus O2 gives me 2 H2O. Can shrink this down now. Move this up a little bit. Okay, let's see what I can get rid of now. My 4 electrons have canceled out. It looks like that's all that's canceling out right now. Let's add up my reactions. 8 Cn minus 4 Ag 4 H plus and an O2 give me 4 Ag, keep forgetting to write that C, Cn 2 minus plus 2 H2O. But I'm under basic conditions, which means I cannot leave this H plus. I'm going to have to add 4 moles of OH minus to each side of my reaction. So plus 4 OH minus plus 4 OH minus. It's going to give me 4 waters, which will cancel out these 2 waters entirely, leaving me 2 waters on my reactant side. And let's rewrite our final equation here. In the end, I see I have 8 Cn minus 4 Ag. Cn minus is aqueous, Ag is solid. 2 waters, liquid phase, 1 mole of O2 gas, resulting in 4 moles of Ag. Cn2 minus, aqueous, plus 4 moles of hydroxide because I am under basic conditions. And that is your balanced equation.